First one is by Akshank Tyagi. So over here. I'll take it to 15 minutes.
Hello, everybody. I'm Akshank Tyagi, a master's student at IISc. So we have already heard a lot of good talks about galaxy mergers. And in the morning, we also heard a talk about gamma rays coming from galaxy mergers. I am working on something similar. I'm working from the X-ray signals coming from the similar galaxy merger systems. And this is an ongoing work with Professor Ranjan Laha from IISc. As I said, this is an ongoing work, so there are not a lot of results as of now, but it's a work in progress. And I'll take you through briefly about what the mechanism is for cosmic reproduction in these galaxy mergers, and then tell you how these X-ray signals are being produced. So just a recap, cosmic rays are very high energy charged particles. It can be protons, heavy nuclei, electrons, traveling very, very fast at speeds of light. And when cosmic rays of energy greater than 10 TeV reach at Earth's atmosphere, they cascade down into producing secondary showers of secondary particles. And as you might know, they are visible across a huge range of energy from GeV up to 10 to the power 20 electron volts, which is much higher than the energies produced by humans at the LHC, 14 tera electron volts. And what you see is that the energy spectrum follows a power law. Now, the source for these ultra high energy cosmic rays is actually still a very big uncertainty. Even though we have known about these for hundreds of years, for almost more than 100 years, we still do not understand what are these cosmic rays coming from. The most well accepted source for cosmic rays is supernova remnants. Shock waves in supernova remnants can produce these cosmic rays, but not at these ultra high energies, which we also observe. For those, we have theorized these cosmic rays being produced in pulsars, active galactic nuclei, gamma ray bursts, and today we'll be talking about galaxy mergers as a possible sources for these high energy cosmic rays. So the mechanism they follow is basically when two galaxies collide, there will be cold ISM gas, which will be colliding at very high speeds. This causes a strong shock wave inside the gas, and this can cause CR acceleration up to Ni energy or slightly above the Ni energy, and this can produce secondary particles. Now, the important thing to realize is that cosmic rays, because they are charged particles, they have a very they do not follow a linear path when they're traveling from the galaxy to us, because they bend in the magnetic fields that are there inside the source galaxy, that are there intervening the galactic intergalactic medium and the Milky Way magnetic field itself. But other particles like the neutrinos or gamma rays that can be produced from these cosmic rays can travel uninterrupted to us. And similarly, my work today is basically looking at the X-ray signals from galaxy mergers, and I use XMM Newton data, which is, I'll talk more about it later. Yeah, so a little bit about the mechanism for CR acceleration. This is called a diffusive shock acceleration. Whenever you have shock waves traveling at speeds much greater than the speed of sound, for example, in a supernova remnant, you can see this boundary, which is the shock wave in blue. This is X-ray image, and the shock wave in supernovas can travel up to thousands of kilometers per second. Similarly, this can happen in galaxy mergers as well. In this mechanism, whenever a charged particle travels across the shock front, it gains a small kick in energy, which is directly proportional to the velocity of the shock wave. This is a first order Fermi acceleration. And when this happens over a very long time scale, the particle keeps bouncing off the upstream and sorry?
Go ahead. It's the lab.
Okay. So the particle, every time it crosses the shock front, it gets a bounce from the upstream or the downstream gas and gains a small energy kick. And over large time scales, it will produce a hard spectral index for these cosmic rays, which is what we require. Now, the important part is to understand what energies these cosmic rays can be accelerated up to. So, taking the fiducial values of the total lifetime of this shock wave and the acceleration time scales, we obtain a value of 10 to the power 17 electron volts per proton. So, heavier nuclei can be accelerated to higher energies, but for proton, it will only be these energies. The important thing to note here is that these protons of these energies will never be able to exit the host galaxy. The Larmor radius, which is basically the deflection caused by magnetic fields, that radius is 0.1 kiloparsec for these energies, which is much smaller than the scale and size of the host galaxy itself. So these particles, cosmic rays, will never reach us. But these secondary particles, the neutrinos, the gamma rays, and the X-rays, which will also be produced in this host galaxy from these cosmic rays, can reach us efficiently. So how are these particles produced? You have heteronuclear PP interactions, which produce charged and neutral pions. Similarly, you have photonuclear interactions, which again produce these neutral and charged pions. And these further decay into gamma rays, neutrinos, and electrons and positrons. So a lot of work has been done on neutrinos and gamma rays from galaxy mergers. You heard Jaya in the morning who talked about these gamma rays cascading down and being observed at Earth. And today I'll be mainly focusing on these electrons and positrons. Here, the electrons and positrons are being produced from these charged pion decays, but also these gamma rays will undergo annihilation from background light and again produce high energy electron positron pairs. And these electron positron pairs will further emit X-rays and radio waves through synchrotron and inverse Compton emissions. So have we actually observed these X-rays? As I showed you earlier, yes, across this shock front in Tycho Brahe supernova, we can observe these ultra high energy X-rays or extreme X-rays, which is basically coming from the primary electrons and positrons being accelerated in this shock wave. What we want to study in galaxy mergers are secondary electrons and positrons, because the primaries will not be the major accelerated efficiently. So the secondary electrons and positrons will be produced in much higher numbers compared to the primary electrons and positrons. And they will efficiently emit radio waves and X-rays because of the host galaxy's magnetic field. So I use XMM Newton data which is a X-ray spectroscopy mission launched in 1999 by ESA, and it has a high angular resolution. It is pretty good for X-rays, 6 arc seconds, and thus it allows us to localize the source of these X-rays better than gamma rays or neutrinos. And now I further go into modeling the emissions from these galaxy mergers. So we look at the time scales at which the acceleration occurs. So the time scale of the shock wave, basically given by the region of the shock wave and the velocity at which the shock wave is traveling in the galaxy, is almost, you can see, a few tens of millions of years. And the time scale for escape of these cosmic rays and these secondary particles is given by diffusion and advection. I'll not go into the details, but you can see they are actually much smaller than, almost an order smaller than the dynamic time scale. As you can see it here, the red line here is the dynamic time scale, which is a few tens of millions of years, and the escape time scale in orange is a million of years, and it is predominant at lower energies for the particles. It is dominated by advection, and at higher energies, it is dominated by diffusion. Okay, so now I want to see what is the spectrum of these electrons being produced, these secondary electrons being produced. Again, a lot of equations. You don't need to worry too much about them. What it basically means is the spectrum of electrons produced is dependent on the gas mass and the Shockwave velocity, and also the pp optical length, which is the distance that a proton or the cosmic ray will travel inside the galaxy before interacting with another proton. So these are this is basically the cross section, the pp interaction cross section, and the pp optical depth. This gives you the secondary electron positron production spectrum. But as I told you, there was also another channel for production of electrons and positrons, which was the gamma-gamma decay. This also produces the similar amounts of electrons and positrons as the above method, but only at energies greater than this gamma-gamma cutoff, which is about 1 tera electron volts. And so this can be modeled as a simple modification factor of chi-e. So this is the final injection spectrum. You can see electrons and positrons are being produced at very high rate across a range of energy at different times of the merger. So in the early times, there will be a steady state, and the constant number of electrons are being produced. And as time goes on and the Shockwave dissipates, the number of electrons and positrons being produced decreases. The emission mechanisms are mainly synchrotron, inverse Compton, and synchrotron self-Compton, which is again an inverse Compton against the synchrotron light being produced. I have modeled all of these, and I have plotted the loss rate versus the energy of these particles. And what you see is that synchrotron has the highest loss rate, meaning most of these electrons are losing their energy through synchrotron, and less by inverse Compton, and least by synchrotron self-Compton. And as you can see, at certain scales, the escape time is actually greater than the synchrotron loss rate. So electrons are also being, at lower energies, electrons are also being lost through advection. Yeah, so synchrotron emission, most of us have seen it, how it is being modeled. This is the synchrotron emission spectrum, and it is modeled using the modified Bessel function. And this is the total flux produced from synchrotron. Yeah. So this is the synchrotron plot. Let's skip this. Yeah. So the two major galaxy merger candidates that I'm working on are NGC 660 and NGC 3256. The radio and X-ray emissions from these two galaxies has already been modeled using this method by Yuan in 2019. And what that shows you is that you can fix the spectrum. This is the X-ray data on red, the radio data in blue, and you can fix the spectrum here to get constraints on the magnetic field versus the spectral index of the cosmic rays being produced. What I want to do is not use radio data and only focus on the X-ray data. So as you can see, X-ray data does not have high constraints in this plot, but it has another advantage. When you go to the parameters of the gas mass and the Shockwave velocity, what you see is that X-ray is independent of the magnetic field. So the X-ray is plotted, X-ray constraints are plotted in pink that do not change as the magnetic field is increased. But radio emissions actually change a lot when you change magnetic fields. So this plot can be done for the same NGC 3256, and you can see again the X-ray emission is a constant with magnetic fields, whereas the radio one changes. Now I'm working on a large candidates, catalogs with almost 30,000 galaxy merger candidates. And I have found out that 162 of them have matching observations with XMM, and I'm working on XMM data to model the X-ray emissions from these 162 matches. So to conclude, galaxy mergers can produce cosmic rays up to these energies, but these energies, cosmic rays cannot reach us. What can reach us are the secondary electrons, positrons, the X-rays being produced from them, and the gamma rays and neutrinos. Lastly, the X-rays and the radio emission from these secondary particles can be modeled, and it will help us constrain this cosmic ray acceleration model from galaxy mergers. Thank you.
We have one quick question. Okay.
Thank you for the nice talk. So you have to have gas in your galaxy.
Yes.
So
So-
have you done that check?
So at least for the first two, there is gas. For the later one, the candidates that I have talked about, some of them are dry galaxies, galaxy mergers. I'm still looking at the classification for those. So exactly. So one thing is, I also want to see how much the gas percentage has an effect on the X-rays coming out of those. So if we can show that if the dry galaxies are even under merger, do not produce X-rays, that will also show you that these X-rays are coming from cosmic rays being accelerated on merge shock waves.
Then the X-rays can come from the AGN activity as well, right?
Yes, so AGN activity can do that. That's why most of these catalogs, I believe, are not AGN candidates. Yeah. So I'm trying to not include AGNs into this as much as I can.
Okay, thanks, Chance. Now
Thank
we'll
you.
go to the next talk, which is by Toushif Alam on feedback.
Oh, he's online.
He's online.
Ah.
Okay, good afternoon, everyone. So I will be starting in a few minutes, or
Yeah, just wait for a minute.
okay.
You have to share the screen. Can you share the screen, please?
Yes, okay. Just give me a moment. Okay. Can you see my screen now?
Yeah, we can see. Just like it full screen.
It's okay now?
Yeah, you can make it full screen, I think. Yeah, go to the presentation mode.
Okay. Wait, I'm in the browser. To
Any problem with sharing the screen?
Okay, wait. Okay, you can see the screen now, no?
Yeah, we can see the screen.
Okay.
Or it's okay. If you have an issue, we can do with that.
This is already in full screen here.
Okay, go ahead then. You have 15 minutes. Thank you.
Okay. So good afternoon, everyone. So today I'll be talking about the evolution of shock and filament structures in the center of galactic galaxy and the numerical simulations. So these are the contents. So I'll also talking about the AGN and the morphology of galaxies and how the filament or thread kind of structures form and how the shock and bubble formation can address the formation of filamentary structures. So for motivation, I have also analyzed the radio data from Meerkat and X-ray data from XM Newton, and I have simulated the shocks. And this is one of the motivation for this work. So this is a ESO 137006 galaxy. This is situated in this right ascension and declination, and it is a very like luminous galaxy in the Norma cluster. And you can see the jets here. This is a F2-like galaxy, and close to the center of the galaxy, there are collimated synchrotron threads. These are called collimated synchrotron threads. You can see these kind of structures, and three are very much prominent. CST 1, 2, 3. They are named as. So how these filaments came to exist there? So that we'll try to understand. So first, so AGN. So AGN are the most of the galaxies contain like very compact region in their core, and they actively emits in all electromagnetic spectrum. And this emission is not just star formed; they are happened due to the accretion into the supermassive black hole. And the yeah, and the most powerful ones are called quasars, and those pointing towards us are called blazars. So, and then the Asian and the galaxies show different kind of morphology like FR1, FR2, FR0. So some examples are here. Where FR1 are like they typically show this kind of structures. FR2 shows hotspots and in the lobe end, and yeah, so they are visible in different frequency regime. And some more examples of filament or threads are for this galaxy, like this is in Abel 194 cluster. So you can see this like this thin structure which propagates very large distances. Like this structure itself is like 200 about 200 kiloparsec. So the origin of the thread or filament kind of structures are varied from uh, case to case. Like for this, the magnetic field orientation is along this direction, and the filament formed in this direction. And here the filaments are formed perpendicular to the jet propagation. Here the filament kind of structures formed mainly parallel to the jets. So it's not like the filament or threads is not like very unique that it should be like this, but it's very arbitrary structure. And then we try to understand like how it can form. So next, so the astrophysical shock and bubbles. So when a jet is like formed, jet is propagated in a medium. So this is the jet opening angle. It formed a cocoon kind of structure because of the forward velocity and the sideways velocity differ, and the material deposited, and it formed a cocoon kind of structure. So the cocoon has like inner and outer part, and the cocoon also helps the jets to collimate by exerting pressure on it. This is our own galaxy image where we see this giant Rosetta bubbles. And So, so from the initial surface, like this is the choked, when the jet is choked. So at the time of the initial cocoon surface, this is the initial cocoon surface. And from it, with the set of this equation, we evolve the surface, the initial shock front, and we get at t is equal to t prime this structure to any other later times t is equal to t whole prime, this kind of shape. So from the initial elliptical shape, it could be formed in this way. These are some more examples of from the initial shock front to later shock front, where in timing of million years. And in the case of supernova explosions, when the initial shape is more like spherical and the shape is more like later times it will form like this. The shape is more mainly spherical in nature. But for elliptical cases, so the shape will be like little deformed and like this. So and then we have compared our uh, simulation with the Sedapteral Blastov equation, and our simulation matches quite closely with the theory with accuracy of this 0.0034%. And how the shock evolves, so I have a video to show like here. So this is how the like from the initial 0 million year the shock front is evolving with time to produce this kind of structure. So according to Sedapteral-Blastov equation, the equation was there, yeah, the blast radius depends on the uh, incident energy and the ambient medium density parameter and time. So this is for different density parameter. Beta is like rho is equal to rho naught r by a to the power minus beta. So density distribution parameter. So yeah, again the simulation matches closely with the theory, and then we try to get the like for the filaments, the confinement could happen. So if the confinement can address uh, magnetic or thermal confinement, can address the formation of filaments. So with this set of equations, we tried to understand, because the cosmic ray electron energy density and magnetic field energy density, these ratios, different ratio of it can answer the observational value of the synchrotron energy we get. And we also calculate the synchrotron cooling time scale, and these are the different combination of the epsilon is the cosmic electron energy density and epsilon be the magnetic field energy density parameter. So so different values of it can address the observed synchrotron power, and but it is highly little unlikely that the magnetic or thermal entrapment can cause the filaments to exist. But then again, so from our simulation we get these results that around at 100 or 120 million year, the structure matches closely with the CST1, the collimated synchrotron 1 structure, and the edges matches on the order of it. And then moving from it, same thing can be done also in the radio and X-ray data, that whether we get to see any uh, radio peak or X-ray dip near to the threads. So this is the X-ray image from XM Newton. On top of it, these are the radio contours, and I have plotted annulus on it, and which is bend. So where the radio threads uh, are crossed with the like in some bin, it is overlaid. So at that point, this is the radio brightness, and extra brightness this is the extra brightness, this is the radio brightness. As expected, we get to see the peak in radio, but there is not like a significant structure in X-ray, because in some filament cases there is like X-ray deep or X-ray excess in those regions, but don't get to see anything of that sort. So yeah, and then we calculate the Eddington luminosity and supermassive black hole mass. So we calculated the AGN cocoon test bubble energy and the synchrotron time, and from it we get to see that the mechanical luminosity is on the order of 10⁻². There is a discrepancy. There could be a discrepancy on order of 10, but still the central supermassive black hole seems to be accreting at a sub-Eddington rate for this galaxy. So overall, the main picture is like how we can address the formation of those filamentary or thread kind of structure. So this could be the magnetic or thermal confinement. This could be the evolution of the forward shock, and those material and that later times can cause the filamentary structure. So yeah, that was the motive for this work, and for more reference, you can see this paper. And this is an archive and MNRS. So yeah,
Thank you.
that's all for me. Thank you.
We can have quick questions. Any question?
Hello.
Yeah, okay, but then maybe I can ask, for instance, like your jets are having very symmetric structure. What is the impact of the ambient medium, like ambient medium density? Is it like a uniform density? Or can you
Here,
try
no.
densities also?
Ambient medium is not uniform. So the simulation we have done, we have taken the ambient density parameter as 0.75.
Mhm.
The density parameter, like the ambient medium, okay, this equation follows for the ambient medium, like rho is equal to rho naught r by r naught to the power minus alpha or beta, suppose. So this parameter alpha or beta, it defines how the ambient medium will vary. So for this case, in our simulation, we take the we fit it with the value of alpha is equal to 0.75.
Okay, all right. Any more question from this side? Okay, if no more question, let's thank Salam for the talk. We have one more talk before we move to the hands-on session. That is by Nehal. Neha. Yeah. Okay.
Okay. So good afternoon, everyone. Myself, Nehal CP, and I'll be discussing on a paper which was recently published in MNRS. And this was done on the bulk morphology studies on dual agent system. It was done under the supervision of Dr. Musmi Das and Dr. Sudhanshu Bhavesh. We have collaborators, Dr. Francois Coombs, Dr. Prerna Vishwas, Anvesh Bhattacharya, and Dr. Snehanshu Saha. So for this work, we had a primary work, which is Gothic. It's a algorithm which was used to detect merging species. Gothic is the short form for graph boosted iterated hill climbing. So what it does is it takes the image does image processing and actively detects the merging species. So it efficiently marks the boundary of a galaxy, and if it detects two peaks within that boundary, it is considered as a merging species. So this was applied on 1 million galaxies from Stripe 82 of SDSS data release 16, and we got 681 galaxies as merging samples. So we did the agent diagnostics on each nuclei. We got that 159 dual agents are 159 of them are dual agents. So since we had so much large data of dual agents, we thought we'll do some follow-up work on that. So agents are likely to be found in mergers than non-mergers, but the environment in these mergers are not well studied in the morphology domain. It's well studied across the wavelength, like in the X-ray, in the radio, but morphology studies are limited. Also, there are well-established correlation between the mass and the bulge morphology. So there is M sigma relation. So if we study enough of the bulge, we'll get more relation onto the central AGN. Also in Gothic, we were able to identify that when there was an SFSF pair, most of them were localized in the blue cloud region. And when there is a presence of an agent in the system, there is a upward movement towards the red cloud region. So when there is a presence of an agent in the system, there is a quenching of star formation. So in order to understand the underlying reason, we thought we'll do the morphological studies on this. So here we are fitting only fitting is the GalFit, and we are using the Sersic profile. This is a general expression, and this is a profile in the 1D as a 1D. And we'll be fitting from 0.25 to n equal to 10 region. So n equal to 0.5 to n equal to 2 is considered as the pseudo bulge, and more than 2 is considered as a classical bulge. For values greater than 2, you can see that there is a bright compact in the central region, whereas the lower regions, it's not that compact. Also, these are the Sersic profiles for different axis ratios. So our methodology was to start off simple. We'll start by fitting only the Sersic first. And if GalFit gave a good fit, we'll consider that as a model. And if GalFit crashes or some unreliable results, we'll give the value, we'll change the model parameters like initial guess values, and we'll refeed it into the GalFit, and it might give good residual. For some sources, we might have to fit an additional structure where we fit it using the exponential. So exponential essentially fits the bulge. So for some cases, we might use Sersic, and one component requires the exponential, or for some cases, both the component might require the exponential function. So we'll do that till we get the good residual and the model is consistent with the galaxy image. So these are some of the outputs we obtained. We fit both the Sersic together. Here for the top object, we are also fitting the exponential function. For the second image, we have an extended tail-like structure here, and it's clearly visible in the residual. We are not trying to fit it properly because we are only interested in the bulge properties. Whatever comes up as a residual is the tidal artifact, and we keep that as it is. So here we have two exponential functions for this profile, and here it's one exponential and one Sersic. Along with these images, GalFit also gives output as this fitlog output, where this is the integrated magnitude of the first single source, and this is the scaled radius. We have the Sersic index directly available, the axis ratio, and the position angle. We also try to minimize this reduced chi-square value we need that value close to 1. So that will be the motive of how we fit the parameter. And since we got that Sersic index value readily available, we plotted the distribution. We obtained that in all three bands which we fitted, like G, R, and I, there was a consistent result that the median value of 3.12 for the Sersic index. And we obtained that in all three bands, we got a consistent result that 80% of the samples belong to the classical region. We went on to do a pairwise distribution setup. Here, the red dot signifies it's a major merger. That means the ratio is less than 1:3. And the blue dot is the minor merger. So the size depends on how intense the merger is. Like if it's close to 1:1, it's a bigger scatter size. And here we observe that most of the blue points are localized in the classical regime, but the major mergers are distributed across the profile. Also, we observe that most of the points lie in the classical region. So this is a distribution we obtained. Most of the objects are in the classical region, and there is a less occurrence of classical pseudo. Also, while fitting, if you use the exponential profile, it's considered as an object with a disk, and all others are considered as ellipticals. We fitted 73 ellipticals, which contained only the Cerseic value, and 58 of them required the exponential profile. And with the from the distribution, we obtained that 34% of them has ellipse distribution, and disk ellipse have 34%. Total, there is 68% almost requires an elliptical bulge in the mergers. So we identified that dual agents are more commonly associated with elliptical or disk ellipticals, which require an elliptical in the system. So these are consistent with the studies suggesting that AGNs are likely to be associated with merger events, and since ellipticals reside in the denser environments, it's consistent with the previous results like A. Dressler. Since we also got the integrated magnitude, we went on to calculate the bulge mass. We took the Bell et al. 2003 paper, and for that we used the color value of G minus R. It was corrected for extinction correction and K correction. For calculation of bulge mass to luminosity ratio in the I magnitude, we get the coefficients of AI as minus 0.22 and BA as 0.864 from the Bell paper. And while doing the mass distribution plot, we obtained that the ellipticals essentially is distributed in the higher mass range, whereas the pseudo bulges are more concentrated toward the lower mass range. There is a clear dichotomy between these two pairs. Also, we consider the major mergers are as those which having a ratio value less than 3, and we obtain that 60% of the sources are major mergers in these samples. So in some literature, they are considering the major merger separation at value 4. If we consider that, this ratio would be 80% and 20%. So from results, we get that agents have a strong preference to reside inside the systems which have classical bulges. Also, the classical bulges tends to have a higher bulge mass system. So this shows us that merging process aids the growth of the bulges. And if you assume that the M sigma relations holds for environments which have interactions like mergers, then we can say that the growth of bulges can be directly correlated with the growth of SMBHs. Also, classical bulges are thought to be those sources which are formed by monolithic collapse of galaxies or major events, the remnants of major events. So it is a redder population, older stellar population. So we saw that most of the samples in a dual agents reside in the classical region. And this is consistent with the results from the Gothic paper, where most of the samples are in the redder part of the CMD diagram. So it is consistent with our previous work of Gothic in the 2023 paper. So dual agents are predominantly associated with mass ratio of less than 3. It's like almost 60% of the sources are in the major merger. So these are consistent with the results of the observational studies in paper of 2021, Testimo et al. So these are it. Yeah.
Okay, thanks, Neil.
So these are the QR for a paper if someone wants to.
Okay, you guys can stand. Time for the questions. Okay, yeah, go ahead.
Yeah.
What was the difference?
Yeah. No, it's like Cerseic.
Then if your case is only for electricals, so 3 components would be.
No, there are 3 nuclei in that sample.
Okay.
Not like. Yeah, that's the triplets in this case.
Also, like, I was just wondering, for instance, if you are fitting a galaxy,
Yeah.
with the center as an AGN,
Yeah.
shouldn't I worry about fitting PSF also?
But it's not that bright. It's like an extended source. We are considering
So
only.
what is the impact of it, for instance?
Like,
Like depending on if I observe the same galaxy with the HST.
yeah, then we
And
might,
how much it affect to your masses or the bulge?
like recently we were doing something with KWST data at Redshift 2, Equesa. There we need to fit it using PSF. Like if there is a
My
bright,
question was like, for instance, if you do, these are local galaxies.
yeah, yeah,
And if I take a, for example, image from HST or even the HSC,
yeah,
then the sender component would animate dominate, right?
yeah.
So
right.
should I worry about how much this PSF component will add to your bulge
Yeah, yeah.
mass and how much it will be effective? That's the question.
Yeah, we would have to fit the PSF as well as the SOSIC, and the combined will be the for the bulge.
Yeah. Any more question? Okay, then we will switch to the next session now. It's a hands-on session, right? Okay.
Yeah, so you can see that.
Yeah, you can announce now. But how many are want to participate? We want volunteer.
Okay, so today evening, there is no dinner, but we will finish around 5 o'clock. So we were thinking if people are interested, we'll have a kind of cultural get together. Sandeep has volunteered to play the flute for us. And if anyone else would like to volunteer or maybe think about it, or people interested, that's
So
one question.
those who are interested then can give their names to Chandra.
Okay.
Yeah, we want more people, otherwise we will not enjoy. We'll enjoy you. Oh,
Okay, so we'll do it after both of the hands-on session, after 5 o'clock. Okay.
yes, to. So yeah, everybody followed the instruction which was shared. I think how many of you are able to install gadget, like just to have a. So are you excited to run your first merger simulation? Because the this workshop title is the Galaxy merger, so I chose that test problem as a running first merger simulation. So those who are not able to install, I will encourage like you can sit close by to the people who are able to install, so that you can also see. Before we start running the simulation, I will just give a brief overview of the code. So yeah, a few of the demos will be given by students as well. So they will explain. I think Aditi will run on the gadget, this simulation, and Harsh whom I showed the work in the morning as well. So he will online show the TNG thing. So he also closely learned all this TNG thing. So he will show TNG thing for 10 minutes, and then Atul Ashutosh, I think you know him. Yeah.
Oh, yeah.
So he will be showing on Gizmo how. So this merger thing. So okay, let's have a brief introduction about this gadget Gizmo, and even I should mention Aripo as well, because all these codes are same. This Aripo, which is used to run TNG simulations. So the basic structures is same, but later on people has like are developing this. So I would say that at the end of this, you should be motivated to develop more codes, develop more of the baryonic physics, which is kind of the state of the art in this area. So we'll start with the introduction of the code, and then the range of problem and scale of problem which you can deal with. So you have to define your problem first, and then initial conditions, what all you will give, and what all assumptions you are taking. So that's where what can go wrong. So the chances are there that many things can go wrong, and you have to be very careful putting in all these parameters. So you have to understand your problem very clearly and defining in a structured manner. And then we'll put the limitation of the previous fluid solvers, because there are many fluid solvers in past decades, but I think this Gizmo one was one of the best one. And later on Aripo is one of the state of the art now. And then people are developing in different part of the groups across the world. So there is a lot of scope. And
So
then
about fire and all, those are also similar? Fire?
yeah, fire is run using Gizmo.
Oh, that's nice.
Okay, this is by Phil Hopkins group
Yeah.
Caltech. So yeah, and TNG is with Aripo, and then all this Simba and Origa. These Origa is also with the Aripo only, with a different version of Aripo. So and then discuss the basic fluid equation and conceptual differences between how you solve the fluid equation using meshless method and moving mesh method and SPH method, which is quite commonly used. And so I will also highlight some of the problem where Gizmo has a more advantage and somewhere it has also disadvantages. And then we'll discuss scaling. You have to usually the problem size is a bit huge, so you have to scale it. So you have to parallelize the code, and you can use efficiently the computations available. So there are some standard scaling tests, weak scaling and strong scaling, where you can test this. And then we'll finally run our exciting merger simulation after this, only 10-15 minutes. So introduction, so n-body codes, it started with Artseth in first, the person who wrote code. And it was like a direct calculation. If there are n bodies, so it will calculate force from individual body one by one. So order of calculation become n square. So it's like a naive way, but for the smaller system, it's good if you have some few thousands and 10,000s of particles per clusters. But when you have a very huge system, as the particle size increases, then your computation time exponential n square, it increases x square, like y is equal to x square form. So that's why people came up with a more smarter method. One of the method was yeah. So what are all possible things you can write? You can use more than one CPU. So suppose you are using only this naive method. So if you use more CPU, then also you can reduce the time, and then you can write efficient codes, and then you can combine above two methods. And that's what this gadget and Gizmo does. They combine all these two methods above two method, where you are parallelizing your calculation as well as you're computing efficiently, where you're reducing the order of calculation from n square to some lower limit. So the one of the method which was developed by Barnes and Hurt was tree method, and PM is the addition to that. which I think combined by Jasjit Bagla in his one of his work. So tree PM is like you have you divide, you take you have a distribution of particles and you divide them into, you put your whole particle into full square, and then you start dividing into four cubes, and you do a same procedure in the next smaller cube like this until you have one particles in each box. So you can make a tree basically. This is the parent cube, and then there are this child cube, and then there are further. So you can think of a tree with the stem and branches, and then going into leaves. So this gives you a handle on how much deeper you want to go in the tree. So basically, idea is to calculate force from a group of particles rather than a individual direct calculation. So suppose if I am sitting here, then I can calculate force due to a combination of all these particles rather than calculating individually. So that way I can save my computation time. So what I will do is, I will not go into further branching into this tree. I will just calculate force due to whole component. So there are smarter method to do that, but this is the just whole idea of that. And PM is so this you can do tree you can do in the smaller scales, like not in the very big scale, maybe galactic scale. But if you are doing large box cosmological simulation, then PM algorithm is where you divide the whole system into cubes and then do Fourier transformation and calculate the potential, average the potential, and you calculate the force. So this is a different algorithm, but the combination of two is a very sweet spot, which gadget use. And then once you have a particle distribution, you can calculate the kernels, basically density. So you want to calculate the quantity like density, and there are macro quantities. It can be temperature if there is a fluid, and it can be pressure. So all these quantities you use a certain kernel. Suppose this is a particle distribution, you want to calculate density at this point, then you use this kernel function, which is basically a weight depending upon the distance. So you will calculate the mass distribution plus this weight. But as you go out, your weight decreases. So this kernel gives a smoothness to these quantities which you calculate. So this is the one of the basic traits of SPH method.
All particles, stellar particle and gas particles, everything.
Yeah, for stellar only density thing, but for gaseous you have pressure, temperature, and.
But this kernel is used for both.
Yeah. So this method is used by Gizmo, Gadget. Yeah, but Aribo has a different method. Yeah, in between you can ask questions because it's an interactive session. Yeah.
What exactly does a kernel mean? What is it exactly?
It's just a mathematical function which it gives a weight. I can write. So suppose my particles are distributed like this. This is my central particle, and this is my kernel function. That is this function form. I can call it W. I can call it WR. This is R, and it's scaled by some softening parameter epsilon. Wherever we want to give a cutoff, basically this is epsilon cutoff. So suppose your particle, this is particle 1, 2, 3, 4, 5. So you want to calculate rho at 0 point, and you will calculate mass depending upon W1. Corresponding to this, you will take this weight, W1 mass of one particle plus W2 mass of second particle, and like that. It's basically giving a weight to each particle.
Oh.
So kernel does the weighting part.
So every point will have a kernel, and then you take the particle according to the kernel.
Wherever you are interested, suppose you are interested in some other particle, then you make another kernel around it.
Why not take a small area where we can have uniform weights?
That is a very simple form of kernel, which there are like cloud in cell, or there are many methods available. That is also used, but that's a very straightforward thing.
But is there, like, when we are trying to do, is there a way on which kernel should we use for what purpose?
This has been a long debate for, I think, 2 decades in 80s, 90s, and now it is settled like this kind of Gaussian kernel, or this kind of kernel. I forgot the name of the person, but this is the one of the famous kernel, and a variety of these are used. This has been long researched as well.
So the kernel is applied after you have done the tree method.
Even during the calculation of the density thing, if at any point, tree is the first part. Then just small introduction about Gizmo, because a gadget, a publicly available code only had n-body mainly, and for baryonic there is a very less physics. It's not very open. It's not an open source, so we have to maybe closely collaborate with them. But Gizmo, some of the physics components are available, so that's why I was giving more discussion about the Gizmo. So, and it's a very versatile code in the sense like it is developed on gadget, but it has a lot of flexibility in baryonic physics. So it is very massively parallel code, and it has a multi-physics component, and it solves fluid equation with the various methods. It depends upon which kind of problem you are working. You can work from very small scale like planetary problems to cosmological simulations. So it's very versatile, and it includes the Lagrangian Godunov method, which is one of the best method to solve the handle the fluid technicalities. It solves fluid equation with the moving particle distribution, and it is adaptive in resolution, basically spatial as well as temporal, and it avoids many fluid solvers has problem with advection and angular momentum conservation, which it handles very well. And I will show 1 or 2 examples just in slides. And it avoids various diffusion errors, which are very common in adaptive mesh refinement. Whenever you have a mesh, then you can resolve, but it leads to some diffusion error. So the gas particle may diffuse from one mesh to another mesh. So that way it is better. And so as I said, that it is inherited from gadget. So it's take the skeleton of gadget and develop on the baryonic part more. So the computation time in the tree method, I think I missed that point. So tree method brings this computation time from n square to n log n, which is huge when you deal with billion of particles. Just calculate. It saves a lot of computation, and you don't lose much on the accuracy as well. So and Gizmo is also improvised version of gadget already. So it also improvises the n-body, like of tree walk, how you walk under tree is optimized, and SPH calculations dealing with the gradient and calculating this density pressure. So it is more refined. So what are this baryonic model? I think where you people have a scope to develop more. So that's why I have highlighted more that you need to. So it has a hydrodynamics option, like if you want to simulate any hydrodynamical system, maybe galaxies, cluster, mergers, whatever, and even this planetary dynamics as well. Then there are many methods like meshless finite volume, meshless finite mass method, and SPH, this smooth particle hydrodynamical, which uses this kernel. This TSPH, PSPH, there are different schemes. I'm not going to technicality, but I have given link, you can go through in detail. And then there are magnetic fields, And one thing is one powerful thing is we cannot simulate cosmological simulations because I said it takes millions of CPU hours for 10 months. I think which we are still developing, but what we can do is cosmological zoom-in simulation, where you can take a part of galaxy and then you can simulate in one environment. That doesn't take much computation. So that you can do here.
That is, so this zoom-in method, that's a whole different thing, huh? I mean, so where will we get the galaxy from? TNG?
Yeah, anywhere. You can get, yeah, you can. So that's what this Fire, Origa,
Ah,
these people do.
so how do you do zoom-in simulation? Can you just describe?
So you suppose you are interested in one galaxy,
Ah.
then you go back to, you trace back those particles to high redshift, and then correspondingly you can generate IC condition in that region.
Okay.
So
And then we evolve, but we have to keep evolving the whole box.
yeah, so one galaxy particles will be in high resolution
Ah,
and other will be in very low resolution.
as before.
You can further reduce, it's your wish.
Okay.
So that way you don't need to spend so much time on the surrounding calculation.
Okay.
So that way we can do more.
More.
I'm telling in the context of our resources availability and more practical things.
This zoom-in takes lot of resources.
No, it's similar to slightly larger than isolated simulation.
Okay, so that is the more practical method now.
Yeah.
Okay, to do isolated galaxy, that zoom-in is better now.
Yeah. That will be more context in that. Yeah. And then you can do, there is a radiative heating cooling chemistry, which is like by ion atom molecules. That is also in itself is a very big field, very evolving field. How you cool the gas, they are very cool. They use the standard cooling function, empirical functions, but still there's a lot of scope to develop if any of you are interested. And then you have a galaxy star, black hole formation, feedback. These are all like in developing phase to, especially in context of the cosmological simulations. And then you can also do non-standard cosmology, like self-interacting dark matter or scalar field dark matter, or any other exotic dark matter you can think of. So you can put it here. Then you can do solid body dynamics, which is more in the terrestrial context. Basically, it is not only astronomy code, but maybe can be used in other branches. And cosmic rays, which is also like developing phase, because the time scale of cosmic ray evolution is a bit larger. So combining this cosmic rays with the baryonic thing is a bit tricky task. So, but it is in development phase. And there are now methods, particle in cell simulations, which are more fundamental, but more computationally intensive. So that require more detailed. I cannot cover now, but they require more detailed analysis. So yeah, so there are much more. I just highlighted few interesting modules. So I will encourage you to develop your own. So what are the limitation with the previous method? The aspirate method, there were many zeroth order error and fluid mixing whenever you're having multiple fluids. So this was a problem with the gadget one. But now gadget is also improved, like 4th version. So they have also worked hard after this gizmo has come. So gadget also has improved now. I think this I'm talking about the older version of gadget. And then you have a finite difference.
Use gadget 4 if there is gizmo. What is the advantage of using gadget 4?
It's like not. It will be more computationally more efficient in terms of like for computational cost.
Okay, computation is cost.
But it is improved in terms of gadget 2, and yeah. And gadget 4 is public, which is I think written by Volker himself. So.
Who is written?
Phil Hopkins.
Oh, that is not public.
No, Gizmo is public. Gizmo, but not the advanced, not the newly developed models like Cosmic Rays, like he's still developing, it's not public.
Ah,
So yeah, not all modules are public, but most of them are public. But non-standard cosmology, you have to, I think, do some work. So yeah, so this code, the one of the interesting thing about Gizmo is it can work like other codes. It can imitate other codes like Pluto, Athena, which are also like standard code used in even like Anjo, Ramses, Flash. So yeah, so it can imitate using, if you use different static grid method and different moving mesh method also. So there are many things. I will not go in very detail now, but overall the gist is that the Gizmo can solve can cope up with many angular momentum velocity diffusion errors. So this is the one of the advantages.
If you do zooming simulation, you will solve it with Gizmo. Better,
Yeah, Aripo also.
Arif also.
Yeah.
Which one is computationally good for like in India?
So that's what I said. Like in Indian context, this anything is good. Like Aripo, Gizmo, there are not much difference in computation.
Oh,
So these are the just like the weightiest. Suppose you want to calculate density here. So this is meshless method, which is meshless finite volume, meshless finite mass method. So this is the weight you give, basically kernel you can think of, and the typically boundary is very hazy here. But moving mesh method, you are making a mesh. It is moving Voronoi mesh. So if the boundary is very clear here, it is adipose thing. And this is SPH method where the boundary is again hazy, very small spherical thing. So this is like different weightage system to calculate the quantities. Shade is basically the weight, just some difference in that. And just to show one example, and the capability of Gizmo is like you start with a Keplerian disk. This is only gaseous disk, and you solve with the MFM, meshless finite mass method, up to you evolve up to 20 orbits. Then you see that gas is more stable in finite mass method compared to volume, and then SPH method is completely worse. And grid method is more worse. So it can handle the fluid very nicely with these methods.
because you're saying the first one remains like that.
First one is the initial condition,
Okay.
and after later on, all the columns are showing the evolution after 20 orbits. So this is just one example.
Second one is MFM is good, no?
Yeah.
It remains like that.
Yeah, it is much better. Now this you might have studied this Rayleigh-Taylor instability where you have a different density components under gravity. So you can see that MFV can handle can show much nice feature compared to those. I think these are all test problems. You can also try. I may not be able to show you, but these are easily achievable. If you can run Galaxy merger, then this is nothing. So just to show codings. So whenever people write code, they check that with the increasing number of CPU, how your scaling will happen. So this is your same problem, but you are increasing the number of CPU. So this is one Milky Way type dense galaxy and dwarf galaxy. So ideally, you should, if you increase the number of cores, your time should not increase. It should be like a flat. So you can see up to 16,000 core, it is kind of flat. It's called strong scaling. And if you increase your number of particles, basically resolution of the problem, this is 32 particles, 256, 2048, and then another some That's for 32. Today for 32 cores. 32. Yeah. These are cores. These are cores and these are number of particles.
16,000 cores is a lot of cores, huh?
Yeah. No, it is not.
98?
Oh, okay. In Indian context, it is.
How many meters? 98.
And we can access maximum of 1,000 over here at a time.
Oh,
Yeah.
oh, that's sad.
Yeah.
You know,
So that's why I said like cosmological simulation we cannot run, but zooming we can run.
Are these problems scaled to GPU as well?
No, these are CPU based code.
Or most of them?
Yeah, these but whatever I'm talking about, Aripo, Gizmo, and Gadget, they are. But Athena, I think some people have developed
Athena has one.
GPU.
Athena don't have, Athena plus don't have, but Athena K, like which is Cocos, it has 100.
Yeah, you use Athena, I think. So yeah, I'm not use it, but yeah.
that's very nice, see? Very nice.
Yeah.
How many cores that one has?
So, those are exact numbers.
1,000. More than, must be more than that. Athena requires lot of cores, no?
It depends upon the problem size. If you whatever problem he is.
I believe that next week,
So,
Yeah, within 1,000 is enough, I think.
yeah, okay.
but
Yeah. Yeah. So yeah, if you're doing small scales simulation, then or the box size is not very huge.
it is
Grid size, basically, how much grid do you use?
so it is,
Then it is easily achievable. Up to 10,000, 1,024, it is easily you can cope up with 1,000 cores. But these are, but yeah, these are different. I think different from this. These are Gizmo where we use this MFV, meshless finite mesh method, and there they use grid method. So both codes work in a different regime. So here the scaling goes different, and there the scaling is more grid dependent. Here it is particle dependent. So if you have a more number of particles, and you are also increasing the number of CPUs, ideal scaling should be like this, and it slightly has, it is much better. So just to summarize, I think MFM and MVM, they are much better method than SPH, which is traditionally used, conserves angular momentum to machine accuracy, and their velocity dependent errors are eliminated, advections are removed, and contact discontinuities are handled better. And this gizmo can be used in wide range of problem from very small scales, cluster, even the planetary things also you can do to large box. And it can emulate many codes like Aripo Phantom. Yeah, and up to some limitation, not exactly like that. And code scales depend upon the problem and whatever resolution you want. So it scales well with the non-scaling relations. And yeah, so it has many baryonic physics, and and it's up to you what you want to develop more. So let's run our simulations. Everyone excited to run?
You can use here only that data. Stop share. Stop share. You can use here to see. Enter desktop PC. Yeah, see. Everything is shared.
Yeah.
Everyone can see this.
No, no, oh, I can see it from here. The picture is- You want to come first? Come first.
I don't.
Can you give me?
Those we can use for
Examine visually, and this is kind of matrix.
Run the control. Yeah.
okay.
Here also you can zoom in again.
That now is result.
Just one time. Just one time. Yeah, that's one. You clear and you go to just to clear, you go to top. Is that clear? No. Just- you can. So now, are you able to, those who have downloaded this gadget and install it, you might have got the executable gadget too.
Yeah, we're in this.
So this they have made a folder to test run, but this executable you might have got in your directory you have installed. So those who have installed, you got it. So you can make a directory called test run, and then bring that executable to that directory, and then you need Galaxy little endian.dat file that will be there in IC folder. You also copy to it here, and then you also need galaxy.make. Make file you don't need, I think, here, but you need only galaxy.param file. That you can also bring it here.
And one folder to get the outputs.
You can make one folder test output where you want to store the output. Let's do one more. One more. Better? More. Next time we'll run Zoom in simulation. You can okay, you can take, we give you 2 minutes to make this folder. So then yeah. So you have to make these changes. Whoever done it, so you can start making these changes. So you have to write down this initial condition file name, and then output directory, which you make whatever name you can take. She took some boring names, but you can take funny name. And then energy. These are the standard things. Maybe first you can do, I can explain later.
file, the gadget make file. Over there in the special behavior section, it says D no gravity, D no deep R&D. So is it like gravity and all those things are by default on, and then we are switching it off, or is there some sort of other setup inside?
In which file?
The main make file.
Make file. So yeah, you have to you have to install with that particular thing as well. Oh, so first open the make file. Just we'll come into that. Galaxy.make. Yeah, so yeah, you need to keep same option switched on. So what is your question? You can
Yeah, so I was asking if you go down a bit. Yeah. Special behavior part.
Yes, yeah.
Yeah, so those are right now, though it's commented out.
Yes.
But in general, what all physics is by default on in these systems, and what is this like that you know?
Oh, so this no gravity means you are if you are solving a fluid thing, so you are removing the gravity calculation thing. You are just solving hydrodynamics. And this is no tree. If you don't want to use tree method, then you use this. And so there are some FFT, TW prefix. You want to use single precision, double precision, so that you can control with it. So you don't want any prefix. So FFTW library can be installed with single precision or double precision, 32 bits, 64 bits. And this is also some SDF pipe library.
Yeah, so these things are like by default on, and now we are just switching them off over here.
Yeah. No, they are not by default on. So we don't need to. If you are only. It depends upon what accuracy and what test you want. If you want to do debug testing, so we use that only for that. But for this, we don't test them more. So these are by default switched off.
What is synchronization? You have put that on. Go up. Yeah, what is this?
This is like because you're running simulation on many CPUs. So if some CPU you're giving some task to some CPU and many tasks. So after a certain time you want to sync all them. So some CPUs have a lower processing speed. Over time when you use CPUs, so they get delayed. So yeah, you right now you can switch on only these. Can you show them again? I think these are there in that file I shared. So have you installed this your gadget with these configurations only, or if not, then use this if you want to run it. Because for every test problem, every problem you have to use different thing. If you are running cosmological simulation, that is a separate. We used to use periodic boundary and other things, but right now focus on this.
Should I go back?
You can show more options.
Make file or file?
This is make files. If you have already used this flags switched on, then you are fine.
Oh, okay.
So how many of you are able to make the folder with the okay, I can also. So if you need any help, I can come also.
So I followed the instruction given in the document that you shared, and the make file looks like that also. Do I have to make any changes?
No.
That's the same.
Yeah. Just we are showing this. He asked this question. Now you can go to your Galaxy.chapter. And whatever areas you should use below, where you are easily part. How many of you are able to make folder with this executable IC in parent file? Okay, then one more announcement is there. So we have shared a sample output through a link to everyone. So at least if you cannot run now because it's like sometime you may miss out, and but you can always watch the recorded video and correct it. So but the output is there, so you can download that. There is a Jupyter file as well, so you can at least analyze and run make some images as well. If you are not able to run now, it's not an issue.
No, there's one command to run. Okay, start from here. Should I start from here?
Despite the keep feeling it's very easy. So it is not like it is not having it. So it is giving the snapshots. There are each snapshot.
So is it fine? Have you made the folder?
I got the snapshots also,
Oh.
but I am not able to visit it because of Python body, Python requirement.
That's fine, that you can resolve later. So yeah, I think we are short of time then. It's a tea time already. So we'll take 5 more, 10 more minutes.
Yeah, it's okay, na? 5, 10 more minutes. Yes.
So if you are able to do that, then you have to just type MPI run minus NP, the number of CPUs your laptop may have. Usually you will have 4 or 8. So you can use whatever. If you have HPC, you can use whatever you have, 500,000. But the Galaxy size, the problem size we should be, there should be that much task. If that is not there, then it will give you error. And then put that / gadget and executable and then param file. And then just click enter. Oh, what happened? What happened?
Lately, I'm running in some other directory. Yesterday, it was running anyways.
No, just find out. Are you using lib? Yeah, so you are not using correct executable. Just you are using the
Like,
previous.
2 executables which we copied yesterday. That was confusing. That I made you.
Okay, you can use the whatever you compiled yesterday. Just copy it here. So yeah, so sometime this errors, okay, I think errors are the part of this coding. So okay, it's occurred. So I knew you are facing that. So if you don't install this library, if sometimes this error becomes with the SDF5 FFTW, that it cannot link well. So this kind of error occurs. So you need to install library on very carefully. I hope many of you might have encountered this error.
I think it's the path in the param file, input and output.
Yeah.
Like, is it the path that is given in the input and output file is correct? Here.
No. Which part?
Input, like it is showing a loading shared library. The errors.
Yeah.
You can check once the galaxy.param file.
No, it is not in the param. It is related to the executable.
Yeah, there were 2, I think 2 similar executables copied and
Do you know which is which?
no, because both were named gadget 2 itself.
There are two. I thought it was one.
Test run folder, there is also one. And
No,
then
where
yesterday,
did you install yesterday?
in this test run,
Test run is inside the gadget.
No, yesterday we installed yesterday this. It worked.
add
Okay, we'll install again. Was SDFI on?
yeah.
Yeah, we are just installing it again. It doesn't take much time, just 2 minutes more. SDFI file DNC. Is off. Let me clean. Why it is again not seeing?
The morning also it worked. But
Okay. Okay, so anyway, no problem. We'll show. Atul, you are here?
Yes, sir.
Yeah, so can you show this running on Gizmo? Stop share.
Sure. I'll just share the screen.
So yeah, we'll show with the Gizmo. I think there is some library issue. It may take another time. I think we are short of time. I will not put more time here, but we can show with the Gizmo. It's the same thing.
Yeah. Can you see the screen?
Yeah.
So once you modify the config.sh file as per the command you want to run, then you have to just make it again. So after you get the executable Gizmo file, you have to like in this directory, I have the executable Gizmo file, and in the example ICs folder, I have the IC file for my run. Then the param.merge, the txt file is the parameter file that I am using. And I will just give the run, then I will explain the parameter file that I am using. So once I start the run, so this is how the output appears. And initially it constructs the tree and all the preliminary calculations. Then after that, you can see it proceeds over the time step, and it is starting from the time 0. And you can provide the snapshot time between a snapshot that it will automatically print the snapshot at that particular interval. So all these things are controlled by the parameter file that you provide. In the parameter file, you provide the directory for the input and the output, along with the parameters like what is the time step between the snapshot you want to choose and the maximum time you want to run. So here I am running the system for 5 gigahertz. And since this is a non-cosmological run, the co-moving integration is 0. So I don't need to set any cosmological parameters. But in case of a cosmological run, we have to like set the parameters as per the cosmological models. Then we can set the softening scales. So in this run, the softening scale for the dark matter component is 1 kpc, and for the star disk or star component it is 400 parsec. So once the the run is still going on, but I have the results with me, so I will just show it to you.
You can show them.
So yeah, so this is the initial snapshot, and the color density is based on the stellar surface density, and the evolution up to 5 gigayears. Here we can see it. The galaxies are coming closer, and after collision, we can see like the distortion of the shapes. And over the period of time, after 3 to 4 gigayears, the disk starts to settle, and like in this run, it is up to 5 gigayears, and the disk has almost settled, but it is not like we can run it up to larger time scales to get a more stable disk.
Okay, I think, thanks, Atul. So we'll show more. So the files you might have got, you can follow now with Aditi. She is now plotting some initial plots which he has shown. So I think the data is stored in binary format. So you can either store in binary, SDFI format. So there are different ways to read. If you want to read binary, this PyNbody is one of the good libraries for n-body simulations, even for hydrodynamical simulations also. And SDFF is a more raw thing. So you need to use H5PY library where you can read all the particles. So particles are stored in different numbers: 0, 1, 2, 3, 4 category. 0 is corresponding to gas, 1 is dark matter, second is stars, disk, and 3 is bulges. That way you can read out the particles. So she's loading. So you need to have these libraries, PyNbody, NP, and plot for plotting matplotlib, and you can load the snapshot, and then you can load the stars. You load from first place. Okay, so don't run now. Okay, so I think maybe the running made some confusion, but this is the way loading. And then the particle number in the disk is 20,000. And for the dark matter, it is 40,000. It's a very low resolution simulation. That's why you are able to run in 10 minutes. And then these are the two galaxies. You have plotted with a scatter plot. You can use your favorite color map.
These particles, these are only scalar particles.
Yes. You can also plot dark matter particle, which will, I think.
So it's
These are dark matter.
gas
So-
particles here, right? It's not
No, in this simulation.
in the simulation.
This is a dark matter particle. So this is just one basic demo. You have more plots. Okay, then I think that's one. We are out of time. Huh?
Facilities outside.
Okay, so we just introduced 5-minute TNG. I think TNG is also important. So Aditi, anyway, you have this Python notebook. You explore it with. If you have any question, ask me, her, or any of this. Harsh or Uttam, you can email. Yeah, you can show and find. So this is another version of movie she made. We don't have much time if it is not. Harsh, can you start sharing the TNG thing?
Yes, sure. Am I audible?
So we will have Harsh. You have only 5 minutes, so please be bit quick. So TNG, which has a, like large box cosmological simulation, how to access its data and just get an introduction. And Fire and Origa are of similar things.
So, am I audible to you guys?
Yeah, can you speak loud?
Yeah, so hello everyone. I will just give a quick demonstration on how to use or access the TNG data. So first of all, you can go to the TNG website. So here we have the data access thing. So you can either access the data through the API access, or like you can see here the key for me, or you can get an access for their Jupyter Labs workspace. So if you just do that, it opens just like this. So I'll just give you a quick overview about how we can access different things. So in this server,
Can you speak
the
loud? Harsh, you're not loud.
uh, hello,
It's fine.
yeah. So while using the server that they have provided, they have several helper modules that they have given to so to ease our work. So we have this groupcat.py and snapshot.py. So these have already predefined functions that we can use, and then we can get the and access the data. So just like that, we can import that to groupcat and snapshots, and this is the simulation directory where all the data for that simulation is stored. So basically, the all the data is our particle data are in snapshots, and all the properties related to galaxies and halos are in the group catalogs. So here I have in the third column you can see that I have the uh, yeah, so loaded the subhalo catalog, and so I only loaded a few fields here like subhalo mass, subhalo position and all, and after loading we can see that in this run, that is this the one I'm using is TNG50, so highest resolution one. So the total galaxies are this much, and then you can also load the header file. So header file contains the all the metadata of the simulations. So as you can see here that the box size is 35 kpc, and all the important data for the simulation. Also, so this fifth column gives all the fields that are stored for the particular galaxy. So if we just print all the fields that are present in the simulation, so these much information is in the TNG data for a particular subhalo or a galaxy. And so yeah, so similarly I have loaded from using the predefined function load halos. So I have loaded the total number of halos in TNG50 and also the subhalos, that is the galaxies. So these are the numbers you can load it. And so this I've used the particular subhalo ID in the TNG50 simulation, and then you can also take out the stellar mass position, just like as I've told you in the earlier. Uh, and you can also we can also plot the galaxies. uh, this is the stellar density plot for this particular subhalo, and like you can see there's the bin size is higher, so you can see it clearly, much clearly in this plot. Yeah, so this is the quick overview like how you can access it. You can access it via server or the API. Server is usually faster and API is bit slower. So yeah, any questions, I'll be happy to answer it.
Yeah. So I think we have not shared this thing, but these tutorials are already available on the website. So it's not something new, but only the plotting thing. I think if you need, I think Harsh, can you compile this and we can share with the participant as well.
Yeah, sure. I will say mail it to you.
Okay, I think it's very straightforward. You need to get access first. So you need to write to the PI. This is Dylan Nelson in Heidelberg. So if you write to him, then you can get access.
You can also visualize the galaxies here. So they have this thing in their server. So like
This
yeah, you can put out all the information here and it will plot the galaxies. And after that, you can have all the information, all the plots for a particular subhalo. So like these are the plots for that particular galaxy that we have plotted. Yeah, that's it.
Okay, I think we are already becoming 40, so let's catch it. Okay, thanks, Harsh. Yeah.
Yeah, thank you.
Perfect.
Should pause. Thank you.
I was just wondering.
Thank you. Okay, I can connect, right?
Not to connect, Zoom your teams.
Okay.
No, correct. Just share the screen.
Ah. Thank you. Let me just quickly go to the washroom and come.
So timing.
Share now. Yeah, we can share. Let me just how do I Zoom link? Zoom link, this link. I don't have it. Was it sent by Maushimi anytime? No, I think not. Okay. Got it. Which one? This one. First one. First. Oh, I need to install the app.
Let's see how.
Oh, then I'll have to install one. This is what this is Fedora. And
But nowadays they're not giving for joining browser. I don't know.
they're not giving.
It's not giving.
Oh,
Because if you use Zoom link, they will get someone else.
it will get downloaded quickly.
Previously it was there. If it is not support app, you can join with browser.
Yes, yes. That is what I was thinking also. But they stopped altogether. They stopped.
But your choice. That is better. You want to show something, second display something. If you share a whole thing, easy to access. Otherwise, you have to stop share, then you have to share the another thing.
Yeah. So you can write to this email address. It will go to the UVIT team if you have any query regarding the UVIT data. Just to get you interested in UVIT, these are some images taken by UVIT, the Big Nebula, Helix Nebula, and M101 Galaxy. And then if you just search in Google UVIT Image Gallery, Flickr, you'll find many more images. You can have a look at it. Now, regarding AstroSat mission, you would have already known, but just to say that it was launched in 2015. Equatorial orbit, 5 payloads, including UVIT. The expected lifetime of AstroSat was 5 years. It was based on the fuel and other factors, but it's still working. Fuel for orbit corrections and all that is still remaining. So as long as the instrument works, we expect the instrument to work for many more years to come. And how to observe with the AstroSat, you can, of course, it is operated as an observatory, and then you can submit proposals. Proposals are called every year, and data becomes public after a proprietary period. There is a huge amount of archival data now, which you can all use. So coming to UVIT, it is primarily an imaging instrument, and there are 3 channels, FUV and UV and WIS channel. The WIS channel is primarily used for tracking, but at the POC, we are thinking about making that also available for the users because it's untapped data, huge amount of data. But that will take time, of course. And NUV channel we lost in 2018. The field of view has a diameter of half a degree, and the spatial resolution is better than 1.8 arcseconds. To give you a feel about the difference in field of view, this is Galax. Field of view approximately 1 degree diameter. That is UVIT half a degree, or the area, angular area subtended by the moon in our sky. But what is great about UVIT is its angular resolution. You can compare the angular resolution between Galax and UVIT here. And another thing about UVIT is that there are filters available in each channel, narrow, wideband, and medium band filters. There are gratings available for low dispersion spectroscopy. And of course, these are twin telescope, of course. One is used for FUV channel imaging, other was used for NUV channel, which we lost in 2018. But there is still a huge amount of NUV data available. So these are all the UVIT filters which are available. You can use them according to your science. And of course, as we progress, there are like 3 different ways of calling the same filter. So in somewhere you will find the filter ID, which goes like F1, F2, F3, and all that in the file names. And in the literature, you'll find names such as silica, NUVB15, NUVB13, and all these things. And that is one way of calling, for example, F1 filter, you can call it a silica. And then there is also N242 WB standardized it, but then the standardized thing also remained, the old method also remained, the filter ID also remained. So if you come across, some people will say that, okay, we use a silica filter, some other people will say that they use the N242W filter, both are referring to the same thing. So maybe this will be a interesting thing to keep in mind, that there are 3 different ways of calling the same thing. So what does UVIT data processing mean? It means that there is low-level data, which you cannot use for science. You need to convert it to high-level data, which is science-ready. And what does a level 1 data, which is a low-level data, contain? It contains 1 second WIS images, which is used for spacecraft pointing tracking, because the spacecraft telescope pointing doesn't remain stable. It shifts, so it drifts, and you need to correct for the pointing drift if you want to use the UV data. So we find the UVIT pointing drift using the 1 second WIS images. And in the UV channel, the detectors work in photon counting mode. Basically, you get time tagged events, and then these are presented level 1 data, but then these UV photon counting data are without pointing drift correction. And in level 2 data, what we basically do is that we correct the UV photon counting data for mainly for the pointing drift, but we also apply distortion and drift what you call flat field corrections. And the UV photon counting data is a primary product, and then from that we derive other products such as count rate and count rate error images and exposure maps. And all these products, level 2 and level 1 products, are sent to AstroSat maintained by ISSDC ISRO for dissemination. This is what we do. And to give you a feel about what does this mean, this is unprocessed data. You can see the pointing drift, the sources drifting all over the sky due to the telescope pointing at all over. And when we correct for that pointing drift, you get the beautiful image. In this case, this is the Wayne nebula. Another case is this NGC 300. Again, this is the blurry galaxy due to the pointing drift, and that is with pointing drift correction. And let's see if we can see this video. So this was one such really bad case of pointing drift. We don't expect this much pointing drift, but then initially there was large amount of pointing drift, which is difficult to track, but then it stabilized. So in some cases, we come across such cases and we deal with them. And another thing is that the astrometry used to be extremely difficult with the UVIT data. And why it is so is because there are very few sources in the FUV image compared to, you can see that, compared to the optical images, which is exemplified by a DSS image. And because there are so few sources in the FUV image, it was difficult for us to do astrometry, but then we figured out a way to get accurate astrometries in the latest version of the pipeline, which I'll be talking about. And we also noticed some other problems. These are rare problems, but then they are there. And then if you're not careful, this can cause problems with the data. For example, centroid gaps, they can appear like a gap in the data, and then they will shift, they can result in split images and shifted positions of sources. So you have to be careful to not include any orbit which is having the centroid gap problem in the data. So regarding the centroid gap, if you go to the AstroSat Science Support Cell, there is a note written on it. So you have to be careful if you are doing your own processing. If you're taking it from AstroSat Archive, that is fine, because we have made sure the data that we are putting out there are checked for all these problems.
Relative offset between the WIS and the FUV, is that constant with time? And if so, why do you have to keep doing astrometry with it?
The relative shifts, there are relative shifts, which affects the PSF also at some point. Yeah.
This is your of the change with time.
It is not large, but it does change.
So they both tighten onto the smooth off.
FUV, okay, with NUV, you can say, they're the same telescope, but FUV and WIS is two different telescopes. So there are some, it's not large, but there are minor shifts, relative random shifts between the FUV and the WIS channel images. It's not large, like it's not huge. It does happen. With NUV, there is no problem. NUV and WIS is the same telescope. And there are also problems like hot pixels, which you need to take care of by masking such hot pixels. So this is just one hot pixel tracing the inverse path of the drift correction, pointing drift correction in the data. So you have to be careful about such things as well and the data. So we take care of all such problems, and then we have now developed a recent version 7 pipeline, UVIT pipeline, and then we have been releasing this UVIT data release version 7, where we have addressed problems in the previous version of the pipeline, and then we have introduced new combined data products. We have improved the metadata, quality metrics, and data accessibility as well. We also assess the quality of each level 2 data set through automated and visual checks. And you can refer to this paper for more details. So as a user, these are the highlights for you for this particular data release version 7. These are all science study data, so you don't need to do any further processing. There are combined counter maps, error maps, expression maps, and events lists. And we have ensured astrometry accuracy through direct and indirect methods of obtaining astrometric solutions. And level 1 and level 2 data. If you have used the older version of the UVIT data, you would know what I'm talking about by clear and concise headers. And so altogether, there are improved organization of the products for easier accessibility and quicker navigation. So these are all the UVIT pointings so far, and more pointings are being taken. So now we get to the hands-on part of this session. We are now transitioning to this new archive called Pradhan, which is hosted by ISSDC, and it was launched in late 2025. And there are already 400 level 2 datasets so far of UVIT, and we are in the process of migrating more data. We are processing all existing UVIT data with the latest version of the pipeline, putting it on Pradhan. And there are 294 users so far, and then I hope that will increase because now you're going to go there and maybe make an account. So those who have a laptop, can you go to this website and then have a look at it? Maybe we'll download a UVIT dataset at this time, and then I can show it to you how the data is. So maybe I can do it along with you. So if you type in Pradhan, you can just search Pradhan ISSDC ISRO, this link will come up, and you will be taken to a page like this. And you click on AstroSat, and then you click on Access Data. Here you would have to make an account. If you don't have a Pradhan account, you just need to make it one time, because if you make an account on Pradhan, you can access Chandrayaan data. Then what else? This Aditya data, Exposat data, everything with one account. So it is better you make an account on Pradhan anyway. Even if you are not interested in UVIT, you might be interested in Chandrayaan or Exposat or anything else which you would like to use. So it is quite an easy registration. All you need to do is provide countless details. I don't know why they want all of it, but you can just provide it and then log in. So what I plan to do is I just plan to take you through how this archive is organized and how to search for data of your interest. And interestingly, this was developed, all this Pradhan interface was developed by one person, and she is doing a fantastic job at doing this. Yes, it does ask for lots of details, but that's how ISRO is. You can actually give some random information. They are not going to check and verify any of it. All that matters is the email, so that you verify it and you remember the password. let me see what will happen to the user stats when you all sign up. So I have a little extra permission, so I'll be able to see how many users signed up. So I can see 295 now. Maybe now that you're finished, maybe more users will be registered. Oh, I can see 2 more people have signed up. 297 now. $298 now, so that is 3 more people. I mean, 3 people. Before this talk, it was 294. So I guess 4 people have signed up during the course of. So I'll wait till this becomes 300 so that I know at least 5 people have signed up. 299, maybe 300. That's good. So I will. 300 for UVIT, but then if you look at the statistics, UVIT is in most in demand. So you can see that. Okay. So let me just go back to this one browse, AstroSat. So you click on UVIT if you get to a page like this. And I hope you are here. I'll give you a moment to get to this page. Good. Anybody facing any problem while signing up? No, right? This should be fairly easy. Shouldn't. Okay, then let me just go ahead. Okay, it is now. This is not like the usual astronomy archives you have seen, and it is. But this is what we get from ISRO, and then I think we should all appreciate what we have. So the way that you search for data in this particular archive is that you can click on. You can search by many filters. There are different parameters. For example, file name, if you know the file name, observation ID, proposal ID, processing level, RN degrees, and RN tech. All these things are there. So let me just show you, for example, one example. I want all FUV observations, level 2 FUV observations, which are meeting a particular condition. So I will say that I want all level 2 FUV exposure times greater than maybe I'll put 10,000. Let's see how many are there.
The object name is not in the drop down.
Object name is not there, but you cannot search by object name as well currently. But then if you click on this info part, source name, whatever is given by the PI during the proposal submission, that will be there in this part. So yeah, so that is another thing that, okay, this is another part which you can find a lot of information. Those who didn't just catch on how I got there, you go to this, click on this info link, this search button. If you click on that, this particular data product meta info comes. Meta info has a lot of information, like what mission is this, AstroSat, what is the payload, UVIT, and what proposal ID, what observation ID, who is the proposer, target ID, source name, which the proposer has given, and start time and stop time if you're interested about like supernovae, and then you want to see when if there is any data during that time, what was the pointing location, and interestingly, it will give you how was the observation configured. In the WIS channel, what was the filter, and in FUV channel, what was the filter. All this information is there in this particular information file. So this is something interesting which you can use. And so now it has listed that, okay, there are some 164 level 2 data sets with more than 10,000 exposure times. So that's a lot. We don't want to see all of that, but you can do filtering like this. So let's see if there is anything greater than 1 lakh seconds, which is quite interesting. There are none. There are very rarely there will be data sets with greater than 1 lakh second, but then 50 kiloseconds there should be. Yeah, there are a couple of very long exposure UVIT data. And then similarly, if you now most of you would want to look at one particular source, right? So what you can do currently, there is no SIMPATH based name resolution or circular window search or anything like that. We have told the concerned ISRO folks that please include that. But till then, the way that you can search for data in this particular archive is that you need to provide the ranges, RN degrees. So you know your array and deck of your source, and then you provide the the range of from and to. So you define a box, and within that box, if there are any observations, it will give you. So you can add multiple filters as well. So for example, this is RN degrees. You can provide deck in degrees. So I'm going to give some very stupid values here, 0 and 10, and some, I don't know, 10 and 20. Let's see if there is anything in that filter. There is nothing there. But you get the idea. Yeah. So now I found this many data by putting in this filter, and then you can keep on adding any number of filters. So now you want to filter it by level 10 FUV having more than maybe 5,000 seconds. So you can do all this. And now let us go to the data actually. So this is how you navigate this archive, which will have this version 7 data products. Now you can download any level 2 dataset you like. I have already downloaded one dataset. I'll just walk you through it because you need to know how the data is organized so that you can use that data. And like I said, it's science ready data, so you can just get to doing your science. So just to show you how the data is organized. So, okay, one more thing that I want to clearly mention is that you would want to use the level 2 data, not the level 1 data, if I have not been very clear. It is there in the file name itself. At the starting itself, it will be level 2 or level 1. Level 1 is without any corrections. So you won't be able to make any sense out of it unless you know what you're doing. Level 2 is the science ready data. So it is a gun-zipped tar file. So you, if you have a Linux system, you know how to untar it, decompress it. It's just tar minus tar space minus XLVF. I'll just show you how to do that. So if you have a Windows system, I have no clue. So you figure it out how to do that. So here, let me just go to the directory where I have kept the data. So I'll just, this is one particular file I had extracted. So let me just delete this and extract it again. Okay, so you won't be able to see the commands here, but I hope you can see now, right? Even from the back, yeah. So the command that you have to put in is, so let me see if I'm in the right directory. Yes, I'm in the right directory. I know the file name. And the command that I have to just put in is tar minus xzvf, sorry, xzvf. You all got it, right? It's a very simple command, nothing big about it, just so that I'm just putting it out so that people who are not familiar with Linux, not familiar with this format can know that. It's just very simple tar space minus xzvf command and do the file name. and it will extract it. And the directory is here. Oh, what happened? How do I get back? Mhm. No, the page close or some unnecessary things. So that
I think your Zoom's quite then.
wait for it maybe.
No, it's okay. You can join from your browser instead.
It's there.
I think it's fine.
Sure. Right. This one, right? Let's read it now. Right. Oh. Okay, I hope you had time to download a dataset if you were able to download it. Otherwise, I'll just walk you through the the dataset I have already downloaded. And if we have time, I will, maybe we can do a fun activity as well. But let's see. So once you have untarred it, you should get a directory like this. So that will have some information like the when was observation start date. So 2016, 5, 18. This was when the observation was started, and then the next thing is the observation ID, and it also tells that it's level 2. And if you go inside, it is UVIT data, and yeah. So all the science ready data will be inside the data products directory. And there is also subsidiary data and information which you probably would not need to look at it, but if you need, you can look at it. And a couple of things you need to know that when you see a readme.txt file, what do? You read it, right? So in order to understand how this data is packed, you just open it. And that tells you how this data is packed. Let me try making this. Can I make it? Can you see from the back, or do you have this file open? It's identical in all the data, but you probably cannot see this. So let me try opening it from text editor. Yeah, this helps. Can you see it now? You can see it, right? Yeah. So this particular readme.txt file has a lot of information, but then how the data is packed and everything. I just want you to focus on a couple of things. It is that this directory structure. So if you are thinking about how the data is packed, this readme file tells you how the data is packed. And then, as you saw, there is a high-level directory, parent directory. Inside it will be UVIT. And if you have downloaded CSVTI or SXD, that will be the file in there. And then inside that, there are data products. And then inside it, there'll be FUV data and UV data and WIS data. This data, as it currently stands, you cannot use it. That's why it has this QL extension, which stands for QL. We're not supposed to use it for science, not yet, but we are working on it to make it science ready at some point. So this data, use it at your own risk. And the NUV and FU data, you can use it. And now there are lots of files. You don't need to be worried about any of it. I'll just explain to you what these things are. So as I said, the main product is the photon events list. So this ce.fits file is the photon events list, corrected events. It stands for CE stands for combined events list. Okay, that's all it says. And there is a lot of string here. Don't worry about it. This is AS1 stands for AstroSat1, hoping that AstroSat2 will be there. And the next line is the observation ID, which you need to put in your paper to tell people that what data you have used. And then UVIT stands for UVIT. And again, this UVIT F means FUV channel, N means NUV channel. Here will be NUV channel. So this is FUV channel. And this PC stands for photon counting mode. Don't worry about the two, that was legacy information. PC stands for photon counting mode. The 00 represents which window it is. Again, I didn't mention it, but then UVT can observe in different window sizes. So there is a default window is all full half a degree window, field of view, which is 512 by 512. But then it can be made narrower, but then your frame rate can be increased. These are some additional details which you don't need to know at this point unless you want to observe a source which is extremely bright, which can saturate your saturate the detector and cause problems. So in such cases, when a supernova goes or something like that, you need to use a smaller window. So all those information is actually here at the bottom, like what 00 correspond to 512 by 512, which is full field. And if you are interested, who is, you can have a look at all those information. And again, so PC 00 stands for the window, and F4, as I said, represents which filter it is. The UV, so this is FUV channel, this is the F4 filter. And then if you remember that table, I hope all of you have photographic memory. That F4 filter corresponds to whichever filter it was. So this is how you make sense of this particular long string. Now I said this is level 2 L2. L2 means level 2 data. C means combined events list. Quite easy, right? Now all the other strings are similarly easy. What if you notice it? There will be img.fits, there are 2 of them. exp.fits, there are 2 of them. There are error file, there are 2 of them. Why there are 2 of them? It is quite simple. One is I underscore L2 image is in the detector system or instrument system. And I'll just get to what that means, instrument system. And A underscore L2 image is in the astronomical coordinate system or RADX system. Now, what is the difference? The difference is that I underscore L2 image means the detector system, that how the image was observed by UVIT in the UVIT detector, the way that orientation how will be the way that it is as it is imaged by the UVIT detector. Now, as astronomers, we would want our RA axis to be falling along the Y axis, right? If your image have astrometry, when you open it in DS9, you would expect that the RA axis is along the Y axis and the DEC axis is aligned to the X axis, right? So we apply rotations to the image, to the data, and then generate A underscore image. So for all scientific purposes, A underscore image and I underscore image, they are exactly the same, except how they are oriented. Now, why did we then keep the detector system images? Because some people who are using, who have specific use demanded that we keep that data. So that's why we are keeping both versions. So now you have understood why there are 7 files altogether. 2 are the image file, and 2 exposure maps are there, and 2 error maps are there, and then 1 combined events list. Now that is for one particular filter in one channel. If there is F1 filter also, there will be another 7 files. If there is F2 filter, there will be another 7 files. So if you have 2 filter in FUV data, you will have altogether 14 files. If you have 3 filters, you will have 21 files. Like that, the number will increase. And same is the case with NUV data. So now let us go to a directory, the actual data, and let's see what is there. So in this case, I'm going inside the FUV directory, and this directory has how many files? 35 files. So there are 5 different filters available in this data. So maybe that will be more clear if I just put it like this. So there is, okay, maybe you cannot read it, but in this directory, there is F1 filter, F2 filter, F3 filter, and F5 filter, and F7 filter. Yeah, there are 5 different filters. And each one filter will have 7 files, and then 7 files, you know what they are. So let us have a look at the image. So image file, you all have DS9, right? So you can just open DS9. So I'll just open F1 filter image. And I will open the A_level2 image. Okay, so image has come. I'll just make it. So you probably cannot see anything there because again, UVIT photon count, it's a photon counting detector, and there are very few photons, FUV photons. But if you want to see what is there in the data, you can do some processing, which I'll show you how to do now. So it's quite simple things which you can do.
So it has some RA data that we should not.
No, astrometry is there for the A_image and I_image. The only difference is how they're oriented. Both you can use astrometry.
So the astrometry is correct.
Astrometry is correct in all of them. It's just that how.
Just all.
How the what do you call it? Maybe I can just show it to you. If you just open it, the north axis will not be aligned to the y-axis in the case of the detector system image. That's the only difference. Yeah. Everything else is the same because we generate both the products from the events list.
Astrometry is correct for both.
Astrometry is correct for both.
Image is rotated.
Image is rotated. That's the only difference. So again, now let me come back to the processing just to see what is there in this data. So maybe if you squint, you can see 3 dots in this data. Let us see if we can make it better. So the only thing that you need to do right now is that you just need to block 2 pixels. So I'm going to this option in analysis called block, and you click on block 2. So what are we doing here is that we are just binning 2 pixels along the x-axis and 2 pixels along the y-axis. So that increases the signal to noise. But then you don't see anything. So what we are going to do, and one more thing we will do, which we will do is that we will smooth the data with a Gaussian. So the default Gaussian, if you want, you can change the parameters, the smooth parameters, but the default values are quite good. The 1.5 sigma is close to the UVIT PSF itself. So now that you have done it, the image, there are more things which are appearing in the data. So you can see more sources. Again, this you do only for looking at what is there in your data. This is not all your science you should do with the actual science data itself. This is counts per second. There is, you can convert it to flex units using the, just take off, there are 0 points available given in the 2017 paper. Or unit conversion if you want it in flex. So 0 points for magnitude, unit conversion for flex. So this is how you look at the data. And then one more thing is that which I want to show it to you right now is the header. So the header will have all the information. Okay, let me make it bigger again. Font, I can make it to 24. Yeah. So all the basic information, so it's all arranged pretty well. So the basic information is there. What is a file name, when it was created, and all those stuff. What is the version, pipeline version? Okay, what sort of data type it is? It's a count rate image and image coordinate system, whether it's instrument or astronomical. And now the important information, instrument configuration, what detector it is, FUV channel, and what is the filter ID. So we provide all three ways of calling the filter. So filter ID, this is F1, and the new filter name is F148W, and the old version is CF2 filter. And whether it is in photon mounting or image integration mode, all that information is there and where it was pointed. And there are some observation identifiers where when it started observing and proposal ID and who is the observer. This happens to be the data for a director, is director and a warning. And this belongs to the open cluster. The observation is open cluster in GC188. And exposure parameters are there, WC's information is there, and yeah, image quality information. So all the header is properly arranged. So it's just a simple walkthrough, but then this is important if you just want to start using it. Now, I think that's all I wanted to cover in the data itself. So you can just play around with the data, and I have 10 more minutes, I guess. So yeah, so there are 2 calibration papers, which is UVIT calibration of the UVIT telescope in 2017 and additional calibration in 2020. Please use 0 point magnitude from London 2020 because I still see some people taking 0 points from 2017. These are the correct, corrected, improved 0 points. So please use the 2020 paper. And of course, you know how to do aperture correction by making cover group or anything like that. That's fine. You do it your way. But then if you're lazy like me, just use this table, which is provided in 2020 paper. There is an encircled energy for each particular radius. So if you are using aperture of 7 subpixels, you know how much encircled energy that is, then you correct for it. If your source is extremely bright, you need to do saturation correction. And if it is bright, you need to do saturation correction. If it is extremely bright, you cannot do anything because there is no prescription for saturation correction for extremely bright sources. So there is a limit. I'm not going to go into the detail, but if your counts per frame is 0.6 or above, you cannot do it. Below that, you can do it. You can do the corrections. And maybe I'll quickly, go through this particular aspect. So UVIT photon mounting has data has time information because it's just time tagged events. So you can do variability studies with UVIT, and there is large archival data sets. So if you are somebody who is interested in looking at UV variability of astrophysical sources, here is a threshold trove, and time resolution of 66 millisecond or better is possible. And there is a software called UVIT, which was developed by the POC. And this is basically just the log of UVIT. You can just, it's an open source Python package. And you can just do a pip install UVIT. You can install it. And it has fairly simple requirements. And there is a documentation in this particular page. It's not updated for the latest version 7. I need to update it at some point, but you can have a look at it. This is the only thing that is required as an input is the events list, combined events list, to work on it. And like I said, it's just time tagged events list. So X position, Y position, and there'll be a time. And this is the events list basically. There are other information also which I'm not showing. And this is the input to the Curvit software. There are two different main functions as part of Curvit. One is make curves. Make curves can automatically detect sources in the UVIT events list data and generate like curves. And curve. For example, you find something interesting that you want to do some, make lots of like curves out of it by changing the time bin and some other variables like background and all that. Both functions can do automatic background estimation, aperture correction, and saturation correction. So this would be a typical workflow where you take the level 2 events list and run it through makers to detect interesting sources. Or if you know already your source of interest, you can just directly get to curve. Or if you find something interesting here, you can also look at it additionally with the curve. And this will be an example run. It's quite easy to run. It's like import curvit.makers. You give events list as the input. If you want the background to be estimated, you put class auto. And it c.fix combined events list. So this is an example makers run, and then it detected some sources and it has created all these like curves, and then you can clearly see here itself there is one interesting like curve here, but there are other interesting like curves also, mildly interesting. This also could be variable. And then if you are somebody who interested, you can write some statistical tests for checking variability of all the like curve data. There'll be the data files also, not just a plot, so you can run your statistical significance techniques on those data files. And this is an example curve run. You can provide the events list again as input. And one more thing, you need to provide the image. You need to provide the source locations in the image coordinates, not in RADEC. RADEC I have not yet implemented it, but if some of you want to implement it, it's open source. You're free to contribute. I would love that. And you can specify the radius, what is aperture radius, and what is the time bin width, and all that. And it will, create products like this. So you mark the source, and it will put an aperture. You may not be able to see it, but there is a black circle showing the aperture. And this is the light curve for that particular source. We know the source is variable. It is an intermediate polar FOAQR light curve. And yeah, this paper is there, Curvit paper, so you can have a look at it. And I think that's it. You can have questions. You can ask questions, or we can do this fun activity which you know afterwards. So please do ask questions if you have any regarding what I have said so far. Okay, maybe nobody has any questions, so maybe we can do a simple fun activity. How many of you have downloaded a UVIT dataset? Nobody has downloaded. Okay, you have. Okay, what we can do is right now is that, see, all of us, this won't be useful for science, but then it can help you create beautiful images for your paper. So if you are using UVIT data, and then you want to create a beautiful image to put in your paper, you can create a beautiful RGB image. So maybe I can show you how to do that in 2 minutes, I think. Chandan, is that okay? Okay, so let's do that. So we will do this with DS9. You can do it also with Python, but I will just show you the simple and quite effective way, which is using DS9. So you will just open DS9. Okay, let me close the previous DS9 and other things which I have opened. We don't need. What is this? Okay, we have our DS9. So the only thing, first we are going to, my computer is a bit slow now, I guess. Okay, so DS9 has come. I hope it won't crash now. So the only thing that you do now is that you click on new frame RGB and a box like this will appear. Many of you may already know it, but then I'm going to just show how to get it done correctly. So it's, if you already know how to do it, bear with me. Otherwise, those who don't, it's a fun exercise. So what I'm going to do is that I'm going to open a WIS image in the red band, or maybe let us just work with NUV and FUV. So NUV image in the red band, NUV image in the green band, and FUV image in the blue band. And that's how we are going to make our RGB. So that is what we are going to do. And I'm going to strictly work with the A underscore images, which is in the ARADEX system or astronomical system. So that's it. So let's start. So I will open it. So first I will open NUV images. So NUV, I'll work with the NUV F2 image. Oh, NUV F2 is alone is there. So NUV F2 A underscore image. And one more NUV F2A underscore image in the green band. And in the blue, I will open the FU image. So I'll just go back and I will include. Okay. So now, I have no idea how this happened. Okay, this Zoom is giving me some trouble, but then let me see if I can click on it. No. Okay, great. Yeah, so even though now it is RGB, you can barely see anything, right? So what do we do to make it visible? We do the same thing as I did last time. It's just that block and smooth. So we will do that for each of the channels. So first we will do for the blue channel. So I'm just going to set blue as current here in this box and view as also blue. So we are seeing the blue and then we are going to work with the blue channel. So we'll go to the analysis and we'll go to put block 2 and we are going to smooth it. Now we can see the data, but you address the contrast and all that, so you can see it better. And you do the same for all the 3 channels. So I'm going to do it in a quick way because I'm going to put it as lock, and then I'll lock both block and smooth operation so that whatever I do to one channel is being done to all the 3 channels. So now that it has been done, probably I can work with the, it has not been. Okay, I'll just do that here because it's not doing it. So I have now done that. And if I now I'll just see how the red band looks. I hope it has been blue. Yeah. So now if I view all three channels together, I get an RGB image. So now you can play with it, make it look better, and then you can put it on your paper. So that's a fun exercise, and I hope it was fun. This can be fun if you work with the Galaxy images. They are quite beautiful. This being an open cluster, it's not that appealing, but UVIT images, as I showed you the this gallery, all those images were made with the DS9 tool, and so go ahead, please use the Science Ready UVIT data from Pradhan Archive. And if you have particular targets which you want processed earlier, because we are currently migrating all the data to there, but if you have some data which you want processed earlier, you can write to that particular email to uvat.atc@iap.press.in. We do prioritize students and postdocs, and then we will make sure the data is available on Pradhan. So with that, I'll stop. Thank you very much for listening.
Hi, Frazal. I have a question, if you don't.
Yes, please.
Okay, so how do you study the background in the image? Like, what is the background in the image apart from the sources?
Yeah, that is a good question. The background does vary. We found that the background does vary across the image as well as with time.
Sorry, your voice is breaking.
Oh, okay. I'll just repeat myself then. The background, UVT background vary across the image as well as across time. So you need to be careful. You cannot use one single background value everywhere. So what I would suggest is that if you're studying for one particular image, you look at how the background varies across the image. You can look at this recent paper by Akshank et al. 2026, sensitivity variations of the UVIT instrument. There we talk about how to create background maps from the UVIT images. Please refer to that paper. It talks about the UVIT background in a very descriptive way. I hope you heard that. Anybody else have any questions? And then done. Okay. Yes, you want me to?
Cultural session?
Yes, we can.
Okay. So anyone else going to give some? Abhinanda, you have today? Okay.